And what we have learned from Knut is that when you look in that the microscope is not just a camera, it's actually quantum mechanics happening in there, and that's very important. And it's also important to when you talk to. You told me once that when you talk to agencies, and like you have to not pretend like the microscope is a camera, because it's much more complicated, and you have to. It's more like a synchrotron or a accelerator or something, and it's really heavy physics going on inside the microscope. So Knut has got the prize for applications of aberration corrections. So he has done a lot of different work. So we will see. It's all yours.
Yeah. Thank you for the kind introduction. This is, of course, the northernmost point where I have ever given a lecture. And throughout my career, I was always interested in learning how the structural properties of a material determine the physical and chemical properties. So the smallest unit of a structure is the atom. So before we started our project at the end of the 1980s, electron microscopy was by far not good enough to resolve the atoms. So collaborating with Harald Rose and Max Haider offered for the first time in material science to improve the optical qualities of the electron microscope to such an extent that you could get access to atomic dimensions. So you see, I'm very careful. I say access to atomic dimensions. I don't say to see the atoms. We're always talking about seeing the atoms, but that's by far not a trivial thing. Or you can say we trivialize seeing these atoms. The reason for this is that the world of atoms is the world of quantum physics. And we can describe quantum physics by means of equations, but in any case, we cannot understand quantum mechanics intuitively on our normal brain functions. Every physics student learns this in one of the first semesters, that you cannot understand quantum mechanics intuitively. Nevertheless, people feel electron microscopy is an exception. No, electron microscopy is not an exception. And we will see during this lecture that we get wonderful images which fit to our imagination. And the reason for this is that I select such images for you. I can show you completely different images the electrons would be very happy with. But your brain always, whether you like it or not, it interprets these images as if they would be light microscope images. So the question is, of course, what is the real looks of an atom? How do they look like, and how does an atomic structure look like as seen by electrons? Because we are using the electrons to explore the structure of the interesting material. So the point is, how can we now, from images which we get in the electron microscope, derive information in a quantitative way? And during my lecture, I will always insist that I want to get out numbers. And not only, I'm not only interested in the aesthetics of looking at atoms, which is its own category. Of course, it has a lot of aesthetics, but those who spend about 10 million euros, 100 It's 100 million NOx, I have learned recently. I think the public can ask for numbers when we buy such instrument. So that means we have to bring the images in concurrence with a quantum mechanical calculation. And how this should be done, and how the experiment should come into these equations, into these calculations, that was at that time, 25 years ago, essentially uncharted territory, was new, and nevertheless highly interesting territory, but that kept us busy for many years, and even nowadays, new theoretical concepts come out in which the people give us better ways to understand the atomic structure. And I think it's also in this third lecture now probably quite useful to give you at least a tiny little feeling about the dimensions. So we have seen a number of comparisons between golf balls or footballs and the Earth and such like this. So I would like to add another one, and this is, first of all, we are now working in picometer dimensions. And we will see very small shifts of atoms in the order of magnitude of a few picometers. And so a picometer is the billionth part of a millimeter. And when you use the number range, it's comparable to the width of a hair to the distance between the Earth and the Moon. So that's enormously small distances. And so it's not surprising that it needs certain mechanisms to understand them. So now let us have a look at these microscopes. On the left-hand side, we see the microscope, which came out of the project, which has been described by Harald Rose and Max Haider, and this was in 1997. So we have a resolution at that time of 0.2 angstrom, and this was a record number at the time, and it doubled the resolution of the uncorrected instrument. This picture here shows you one of the most modern microscopes, and this has a resolution of 0.06 nanometers, and we have therefore a doubling of the resolution as well. Now, when you will see during this talk now, also when Andrei Krivenek comes up, that we have two modes of electron microscope operation. The first one is the so-called conventional operation-corrected electron microscope, where the image is formed in one shot, as if it would be in a camera. And the second mode is the scanning transmission mode, in which you scan the sample by a fine electron beam, which also determines the resolution. And this operation correction of STEM was pioneered by Andrei Krivenek, and I think we will hear about that in the next lecture. Now we have, when we have the microscope, we have, of course, to have samples fitting into the microscope. I will only talk, by the way, about conventional operation-corrected transmission electron microscopy, and leave this to the next speaker. So we have samples which are extremely thin, about 5 to 50 nanometers in thickness, and we mount these into tilt goniometers. That means we can align the samples in such a way that the atomic rows are going along the viewing direction. That means we align the sample in such a way, which I have sketched here. That means when we look at these images later on, we have in most cases other atoms behind the particular atomic sites. So now let's start as we did it 2.5 decades ago with strontium titanate, which became more or less the Drosophila of material science, operation-corrected electron microscopy. We have the individual atoms here in this ball and stick model, strontium, oxygen on the faces, and in the middle we have titanium. We will, in all the images you are seeing, we will look along this direction. That means we get a projection which looks like this. So we have strontium, and behind each strontium is another oxygen. And that means we have strontium rows, and we have rows where we have titanium, oxygen, titanium, and so forth. Now we put such a sample into the microscope. And these are image simulations which show us the images you get as a function of the focal length of your lens or the thickness of the samples and other parameters. So we have just seen the structure, and now look at these images. So the question is, which is the right one? All these images are the right ones. None is wrong. Every image contains all the information of the sample, but it doesn't fit to our brain. So we just can say, okay, is it this one? No, doesn't fit at all to what I have just shown to you. And so it goes on. All these could be the image, contain all the information, nothing lost, or even this one. Or this one. Many more dots than we are expecting according to the model. So that's the reality of atomic resolution electron microscopy. And I normally, since I know that, in this particular case, we know the structure. We know easily, we can find out easily which one fits most to our imagination. Again, each one is correct, but it's inconvenient to deal with images like this because you cannot easily, your brain is not capable to see the atomic structure there. So this one is the one which fits most. So when I talk to you later on, I will always refer to images like this because they fit more to our intuition, but I just selected it for you, because I don't want to make problems in your brain by showing you these images. But anyway, this is the type of image. That means in the following we will normally pre-calculate the images, and then I show them to you. So as long as the structure is known, everything is fine. Easily you can find the right condition. But when you have structures which you don't know, this is really a problem. It's not easy to find out for a structure which you don't know what it is really looking like in the microscope. So now this is the image in the electron microscope. So we see all the atoms, we see the strontium atoms, the titanium, we see very nicely the oxygen atoms. And images like this were considered a sensation at the time when we published them. There were people writing comment articles and so on. So everything was fine. And I think even you, as I do, I like the aesthetics of an image like this. So that's how nature looks like in atomic dimensions. So wonderful, everything super. Yeah, but there is a mistake in the image, which you don't see so easily before I tell you where it is. Look, we have the titaniums aligned with the strontium atoms. Very straight line. And now look at this here. The strontium atom is moved out in this direction, the titanium atom. So next Kavli price, or even higher, because we have discovered something. You see that the titanium atom is shifting to the left by 30 picometers. When you have a microscope where you can essentially measure a few picometers, this is very, very wrong, or maybe the next price. And of course, it's not dramatic because it's trivial what has happened here. The sample is tilted. Because I told you that you have to align the atomic rows in such a way that you can look along them. So you do that. But when you have in atomic dimensions some 10 up to 100 atoms to align perfectly, this does normally not work. You have always tilt in your samples, because we use normally a mechanical tilting device, and this is not arbitrarily correct, precise. Therefore, there's always some tilt in the samples. You can say, yeah, okay, we have we just have a projection factor, and that's it. And now that's the trick nature and quantum mechanics are playing on us. The shift for the individual atom is different. It depends on the nuclear charge of the atom. So the shift of strontium compared to that of titanium is different. So titanium shifts for this 5 milliradians tilt, shifts a little bit more. So this is the result of the waves, of the electron waves going down the atomic channels, and the quantum mechanics is different, slightly different quantitatively for titanium and strontium. So here you really trusted your eyes. You felt you see everything, but the image at least contains some interesting features. So when you look at individual atoms, the easiest question to ask, is there an atom there or is it not there? This is part of the work we have done in my superconductivity group, and we have looked with the electron microscope into yttrium barium copper oxide. It has a superconductivity transition temperature of 92 Kelvin. This here is a ball and stick model of yttrium barium copper oxide. And we have 3 perovskitic unit cells which together form the unit cell of yttrium barium copper oxide. We see here the barium, yttrium, barium. Green are the copper atoms, and blue the oxygen atoms. So it's well accepted nowadays that the superconductivity is a whole superconductivity along these planes here, and the doping of these planes with holes goes via these copper-oxygen chains, which is an elementary factor in this type of superconductivity. So there's one important point here. You see these crosses. And the theory of high-temperature superconductivity for yttrium barium copper oxide postulates that the positions here at the crosses are not occupied. There should be no oxygen atoms. And so the question was, can this be shown experimentally? And at that time, when we did the first experiments with yttrium, barium, copper oxide, of course, operation-corrected microscopy was not available, and we had no chance to see whether these sites were occupied or not. So, after we had about 15, 20 years later, the operation-corrected microscope available, we put a sample here into the microscope, calculated the conditions so that we have essentially a view which is easy to interpret. Here we have the copper atoms, here we have the barium atom, and we see the oxygen here, down here and up here. So we are looking from this direction, so we see the oxygen. And now we tilt the sample by 90 degrees in the microscope, which those who do this know is not trivial, because you also have to align your atomic rows perfectly and so on. So such an experiment is not easy to perform. So this is one of those which worked. And now we tilt by 90 degrees. We now look along this direction, and the oxygen is gone. So this is a direct proof for this copper oxygen chain theory. So atom there or not there, that's the easiest question. The other thing is whether the atomic concentration in a given position is the one you expect theoretically, or the one which you like to have for a particular device function. And one of these cases is barium titanate. Barium titanate is a technical dielectric which is frequently used in technology. And people found out that when they produce these devices from thin layers of barium titanate, that the electrical properties were much worse than what they had expected. People had a lot of discussions about this for some years, and many ideas were put forward. And one of them was that the thin film layers would show a twin structure, and inside the twin structure, the stoichiometry of the layers of the films was disturbed, and it was postulated that you have less oxygen there. That means under stoichiometric oxygen concentration. So now with the operation-corrected microscope, we could for the first time see the oxygen. Before, nobody could image oxygen. And here you see the oxygen again. The arrowheads point to the oxygen atoms. So now I have just said that we look along the atomic rows, and we now calculated the intensity, the expected intensity of the oxygen atoms as a function of occupation of these atomic rows. So each of these white spots here is a missing oxygen atom. So for all different concentrations of missing atoms, or the different numbers of occupied sites, we calculated the intensity. That means we have here plotted the occupation. 1 means full occupation, 0, no oxygen there at all, and here we have the intensity. And this then we compared with the quantitative measurements in the images, and here we have the oxygen results. This is for barium as a control test, and this would be 100% oxygen, and here we have 50%, and you see that the concentration of oxygen is reduced. Only 68% of the oxygen sites are occupied, 32% of them are left vacant. This can be explained by a valence analysis. When you want to accommodate more than 32% of vacancies, then the structure of the compound collapses. So that can be all explained, but this is not what I want to talk to you about, because I think it should be easy to follow. We don't want to go into all these details. We also measured the atomic distances in these twin boundaries, because this was also for a long time a matter of controversy. And so we did measurements of this is the twin boundary, and now we measured the distances, for instance, for these two titanium atoms, or the green ones in this case are barium. So we see that we find that the titanium atoms are shifting apart by 35 picometers. The barium atoms are moved together by 17 picometers. Wonderfully small numbers. So I really like these small numbers. And there were also other people later on. So that's the experimental results. That's the measurement in the images. And then a theoretical group in US, some years later, they did a first principles DFT calculation. And when you compare the numbers, they agree to the third digit. So these things are in resonance with each other. And I think that's the fascinating point. Atomic resolution microscopy like this fits directly to the DFT calculations. That means it fit to the solid-state theory of our days. So really these two can communicate with each other, and we can, first of all, we can give them numbers to start their expensive calculations and time-consuming calculations, and on the other hand, we can give a mark, a stone, orientation stone for them, whether, or they also can do this. For us, I think this cooperation is a really good point. So at this point, I would like to come back to what I have said in the beginning, and this is that you can only trust these images when you do the calculations, and we have already seen that this trust is the key point in quantitative electron microscopy. Nevertheless, I'm always showing you these images. We have agreed that I have to show these images to you because these are the only ones which you understand. I think I don't want to go into further details with that. So I show you these images because they fit to what you think about it. And so I now continue with other nice images. This is magnesium oxide. It's a nanocrystal. Nanocrystals are used in catalysis. And the individual sites on such a nanocrystal, they are the sites where the catalytic action occurs. So this is an interesting topic. This nanoparticle, this is one of the images of one of these nanoparticles, shows various intensities of the atomic points. These points here are very strong, very bright, but there are others here which are very mild in contrast. Some are extremely weak, like this point here, and from the intensity evaluation of this, you can now determine not only the shape of the crystal to single atom precision. We can also, in suitable cases, we can identify the atoms when they are not magnesium oxide. Magnesium oxide has always the tendency to be covered by carbon. The reason for this comes from the manufacturing of the crystals, and the other is that there is a strong chemical force which leads to the fact that some of the magnesiums are occupied. The magnesium sites are occupied by carbon. Carbon has 1/2 the nuclear charge of magnesium, so this should give us a weaker contrast. So in all, we can determine the three-dimensional shape of this nanoparticle to one atom in precision, but as I said, not only atom by atom, we can also talk about the composition on the surface in this way. So this is this area here, and this is how the projection looks. So look at this atomic row here. You see that these 4 atoms, they are inclined to the right. And this atom here is just shifted by 20 picometers. And you see it by your eye directly. Now I come to my 2 final examples, which move us more close to application, to useful things. And here we are talking about ferroelectrics, a brief introduction to ferroelectricity. So we have so far talked about neutral crystals on the unit cell level, these perovskitic oxides which I have shown, barium titanate, strontium titanate. We have the situation which looks like this. The positive charges of the cations, their center of gravity is just coinciding with the center of gravity of the negatively charged oxygen atoms. So the 2 centers of gravity coincide. On the unit cell level, this is electrically neutral. In a ferroelectric material, you have all kinds of atom rearrangements. In our following case, the oxygens have shifted upward here, so that the center of gravity of the negative charge has moved upward, while the cation lattice in a first order has remained untouched. So we have here no agreement between the 2 centers of gravity. So we have on the unit cell level, we have a charge distribution, and in this case then a polarization, a dielectric polarization. We again are looking along these projections as before, and we see here the oxygen atoms shifting upward in this sketch. And now we look at the on lead zirconide titanate, which is also a fairly frequently used technical dielectric. And we magnify these images here, and you see directly that the oxygen has moved up here out of this zirconium titanium row. And we now go to the other side here, and we see that the oxygen has moved down. That means we have 2 polarization domains, and this is the polarization domain boundary. And in the boundary, the polarization direction changes on a very short distance, about 1 to 2 projected unit cells. So what is the nice thing here is that we see directly the shift of the oxygen atoms by 30 picometers up or down. And this can be used to do a electrical function. When you have chip cards in your pocket, bank cards and others, some of them store information in the form of such polarization patterns. That means an everyday life function is based on shifts of oxygen atoms 30 picometers up or 30 picometers down. These are the ferroelectric random access memories. So we just here take oxygen up as a binary 1, and oxygen down should be a binary 0. Now we apply an electric field. The domain wall shifts, and we inscribe in this way a binary 1 to the other side. Now my final example is about superconducting quantum interference devices, abbreviated by SQUID. The SQUIDs are working on the basis of the quantum mechanical Josephson effect, and we have, in my own group, we have worked, we are still working on this since a long time on SQUIDs, working on the basis of the Josephson effect in yttrium, barium, copper oxide. And in our case, the heart of the function of the SQUID is a grain boundary. In this particular case, it's a 90-degree tilt boundary. That means the unit cell of yttrium, barium, copper oxide here is tilted by 90 degrees with respect to this unit cell here, and here we have the tilt grain boundary. And since a lying unit cell of yttrium, barium, copper oxide does not have the same lateral dimensions as 3 upright standing unit cells, we have problems here. We have a misfit, and the misfit has electronic consequences. You also have changes in contrast here. I don't want to go into detail here, and I show you one of the earlier measurements we have done on this, and here I only concentrate on 2 atoms. The yttrium atom is small. It's pushed into the grain boundary by 9 picometers. Since it's an early measurement, at that time the measurement precision was only 4 picometers. We can do better today. And the big barium is pushed out of the boundary by 11 picometers. Fantastically small measurement values which we can measure. Now, this boundary is the heart of the 2 weak links in the SQUID loop geometry. This is a light optical micrograph, and this is the whole thing after packaging. We have 2 geometrical arrangements, and here you see magnified the SQUID loop again, where in here are the Josephson junctions, and we now mount this into a scanning device working at liquid nitrogen temperature, and we can measure now at the Berlin Charité, we can measure the heartbeat magnetic field of a human patient. So this is the world record in sensitivity of such devices, which I think we could achieve because we have this atomic resolution electron microscopy available. So I wanted to show you that this is useful. I thank you for the hospitality, the Kavli Foundation for the prize, and you for your attention. Thank you.
Thank you, Knut. We have time for one question. Yeah. Oh yeah, we need the microphone. There is. Yeah.
My question is okay. Has to do with the vibration of the atoms.
Yeah.
You see in the pictures they all are fixed, very beautiful. Is this done at low temperature, or the vibrations are averaged in the image?
So that's not done at low temperature. These images are not done at low temperature. I think we touched this, he pointed this out yesterday, that the atomic vibrations are a limit to the resolution. I think I always talk not about resolution, I talked about precision. So resolution is fine to characterize a microscope. That means you have two atomic contrasts which overlap and then you put them apart until you can separate them clearly. That defines resolution. But what can you do with resolution? Nothing. The real measurements mean that you measure the distance between a reference point in your sample and another atom. And this is not dependent so much, it's dependent but not so much on the optical qualities, it's dependent on the signal-to-noise ratio of your contrast figure. So if the atoms are vibrating, this is not affecting the precision of this because the digital recording of this is evaluated then by the computer measuring the individual intensities, and then we determine the center of gravity of the intensity of these. So this is the thermal motion, let's say, is not so much a problem for these type of measurements.
Okay, thank you again, Knut, and it's a small gift from NTNU.